So the recording has started, and can you confirm if you can see my screen?
No, I can't see the screen.
Okay,
Yeah, yeah, I can. No.
you can. What about now? Can you see the slide?
Yes, yes.
Okay. So it's been a long time since we met and uh, discussed about the tissue engineering topics. So let me quickly remind you what we did in the last class. We started with the broad topic of biomaterials, all right, and we have already finished up the cells part, like what type of cells we can use. We have discussed about stem cells and how do we culture those cells. Also, we have looked into the fundamentals of cell functions, like the dynamic state of the tissues, then cellular fate processes. So we have already covered the cell biology part, you can say, of the very broad area of tissue engineering. So and we have started with the materials part. Means tissue engineering also composed of a very sub area, that is of material science, and that too within material science we are only focused on the special class of material called biomaterials, because these are the biomaterials can only support cell growth, not the other materials which are there. Okay, so we have looked into what are classes of biomaterials are there, right? And the properties that one should look at, like the bulk properties, the surface properties, etc. Then how do we characterize these properties? The techniques we have briefly looked on. So and from today's class onwards, what we will see how we can use these materials to make the artificial ECM, or also known as scaffolds. Okay, so we will so without scaffold you won't be able to give the cells some mechanical support onto which they will adhere and grow. That is why it is an important topic to discuss when you're talking about tissue engineering. So what is scaffold basically? So scaffold is a three-dimensional structure. It is usually porous, means it contains tiny macro or sub macro level pores. Okay, and they can be also fibrous in nature, like in like textiles you have seen small threads are there. Similar kind of structure can be there in a scaffold, and this material they should permit the transport of liquids. Okay, so whatever nutrient media or whatever gas is available, like CO2 and oxygen, transport should be possible. If it is not possible, then the cells won't be able to get the nutrients and the oxygen needed for its survival, okay, for doing all the metabolic processes. And they should promote cellular interaction, means on this scaffold the cells should be able to interact with one another, right? So only then the like all the growth factors or the signaling molecules, etc., will be released, right? And we will be then able to mimic the in vivo microenvironment in vitro condition. It should also promote cell viability, right? Means for if you are culturing the cells on the scaffold, they should continue to get oxygen and nutrients so that the metabolic processes continues and they continue to survive. And these cells, so these scaffolds, when implanted in the body, they should promote minimum inflammation. All right, means our body, we are the host on which these cell containing scaffold will be implanted. So our body should respond to it with minimum defense mechanism. So we will talk about host and material interaction, how it happens. Okay, and it should not be toxic to our body, right? So when it like this material should also have a biodegrading property, means the scaffold or the whatever material that you have used to make this scaffold, it should biodegrade, means over a period of time it should start to break down into smaller pieces, okay, or into simpler molecules, which are not toxic to us. So usually the byproducts of this biodegradation are usually oxygen and water molecules, which our system can easily pass out. Okay, so that is why often they are not toxic. These byproducts are not toxic to us. Okay, and also one should note that the rate of biodegradation, it should match the rate at which the cell is going to secrete its own ECM molecule, because if cells ultimately need an ECM, so initially we are providing scaffold to as an artificial ECM onto which the cells can start their function. Okay. Now, once the cells have started to grow, they will, over the period of time, try to degrade the artificial scaffold and secretes in own ECM. So, this rate at which the ECM is deposited and the rate at which the scaffold is degrading, they should be like almost equal to each other. Otherwise, if one is happening at a faster rate than the other, then we won't get the desired result, okay, from the scaffold that we are using. So why should one fabricate a scaffold? So I have briefly told you that initially when you are adding cell suspension, you want and you're using a cell which can only grow if they are in adhered state, then you need to give a mechanical support. So these scaffolds are acting as a mechanical support for these cells, and often the material that you use to create these ECM or artificial ECM, they are derived from mammalian tissues. Okay, like they are often composed of collagen or fibronectin, hyaluronic acid, etc. So these components are often available in the body's tissue. So you are trying to expose the cells to similar type of material that they are already familiar with. Okay, so in this way you can create in vitro the body's microenvironment, okay, using these scaffolds. So for these two reasons we need to fabricate a scaffold. All right, any queries so far? I hope you're
Ma'am, can you say
yeah.
the repeat the two properties?
Okay, so I said why we were discussing actually why we should fabricate a scaffold, why there is a need of it. So first purpose is to provide a mechanical support for the cell to grow. And it is important when you are using a cell type that is of adherent nature. Okay, so you need to provide it a substrate. So that is why scaffold becomes important. Another reason for using a scaffold is suppose you are using that material that is already found in the native tissue, right? Like you can use collagen or like a derivative of some collagen or hyaluronic acid and other type of materials which are available in the body's tissue. All right, and you're making a scaffold out of these material, then what happens, the cell, since they know these materials to be found in their tissue and you're artificially providing it, then you're be able to at least at some to some degree mimic the in vivo microenvironment in your using your scaffold. Okay, so that is the
Okay, ma'am. Okay, ma'am.
all right. Now, what should be some basic properties of a scaffold that one should uh, keep in mind while making it? One, it should be biocompatible, means whatever material that you're using to make the scaffold, it should be biocompatible, means most appropriate for the application for which you're making the tissue after all. then it should the scaffold should have a high surface area to volume ratio. Okay, this is important because if the surface area to volume ratio is high, then you can load more and more cells, then you can get a higher cell density, and then the you can achieve that clinically meaningful cell numbers, right? That is in million to billions. That cell number you can achieve if you are seeding the cells on a scaffold which is having a higher surface area to volume ratio. Then it should also have pores, not just pores. The pores should be interconnected to each other, like tunnels, like these are called tortuous basically. This is one pore, it is connected to this with the tunnel, this are another pore, it is connected to another pore, just like that. So they are like interconnected through a very tiny tunnel system. So this kind of interconnectivity in pores will basically allow better cell infiltration. So if one cell has adhered at some location of the scaffold, through these interconnected pores, it can travel to another location, right? And if you are going to use this uh, prepared tissue engineered construct on a body, ठीक है, on a mice body or on a human body, then the body's blood vessel, the microcapillaries, they can also infiltrate better and interact with the cells that are there in your tissue construct and provided nutrients. So basically for the transport purposes, it is very, very important to have an interconnected pore system. Then the biomaterial that is used to make this scaffold, it should have, or the scaffold should have the appropriate shape, means whatever shape uh, so whatever tissue for which you are making a tissue construct, artificial tissue construct, it should mimic the tissue architecture of your tissue construct, should mimic the tissue architecture of say bone or skin, like your tissue of interest. The tissue architecture should be mimicking. So your scaffold should be made to mimic the tissue architecture of your organ or tissue interest. Okay, so these are the four properties that one should have in mind while making a scaffold. So if there is any queries, let me know. All right. So there are various techniques through which you can prepare a scaffold. So these are some traditional ways of like traditionally means these are some of the ways through which you can like make a scaffold. Although this list is not an exhaustive list, it only contains the names of the techniques that are most widely used. So first you can categorize a group of techniques under leaching method, like solvent casting, salt leaching, ice particle leaching, gas foaming, and salt leaching. So these are the leaching methods. So here you will see that some component is basically leached out. If you understand the term leach, so it is basically leached out to create a porous structure. Okay, porous 3D structure. We will look into two examples of this category. One is the solvent casting salt leaching, another is the gas foaming salt leaching. Then it will become more clear. Then there is another group of techniques that is called microsphere technique. So here people make microspheres, that is basically spheres that has a size in the micron range. All right, and they can be either made up of biodegradable materials, so it is biodegradable microspheres. Also people make macrospheres, means that are like in the range of millimeter to centimeters, right? So these are macrospheres, very, very big spheres. And also people use the technique particle aggregated scaffold, so it is particle, not particle. Okay. Next group of technique, so here we will like briefly touch upon how people are using these micro or macro spheres, like the general principle of this particular group, and a few examples and images. And then we will also discuss another group of technique that is called phase separation method. So here people take advantage of the fact that uh, two phases of matter like liquid, so solid and gas, or liquid solid, so you can separate these phases from one another. Okay, and create completely two distinct phases, like one solid phase or one liquid phase, or gas phase, or a liquid phase. So in this way you can separate the phases, and in one phase you will get a solid construct. So um, we will only discuss about the freeze drying method, where you will see this process of sublimation is going to help us to create porous architectures, porous tissue engineering scaffolds. Okay, then there's a fiber spinning method, where this method, or this group of method, is developed by taking inspiration from the textile industries. Okay, because our tissue, like muscle, if you say for example, have a like fibrous structure. All right, and if you want to mimic that kind of structure, people have using fiber based methods. So one such technique that we will look into is electrospinning, but there are other methods as well, like wet spinning, then non-woven PGA fibers. So we will only look at electrospinning. Then people have also used decellularized matrix. So basically here what people are doing, they take say exogenous tissue, like from an animal like pig, cow, etc. So take that tissue, okay, and then remove the cell, okay, all the cells, and what you will be left with is only the ECM, and on this ECM they seed the cells of interest. So that is called decellularized matrix. So it is advantageous because uh, like all the in vivo ECM components you are getting in the 3D structure. You don't have to individually arrange these materials, or you don't have to individually mix these materials to get a 3D structure. Here in correct concentrations, multiple materials are already available in your decellularized matrix. So that is one advantage. Then another new field, basically new way of scaffold fabrication, is 3D printing. All right, so this is taken from the people who are like working on an additive manufacturing. Okay, so this is an additive manufacturing technique. So here the materials are added layer by layer to create the final 3D structure. So under 3D printing, you can like various 3D print technologies exist. Like you can create a 3D structure by putting drops on top of one another. That is inkjet printing, it is said. Then you can use lasers, all right, to like cross link your material into a 3D structure. So layer by layer, the laser will be falling on and the material will be cross linked, and you will get a 3D structure. Then you can extrude a material, filaments, and form filaments. Okay, and they'll be deposited line by line. All right, or you can also use cell electrospinning, where so basically this technique, cell electrospinning, is coming from this technique electrospinning. All right, where you create fibers, but within the fiber the cells are also there. So we will only discuss 3D printing, and like comprehensively discuss what is called 3D bioprinting. Okay, and I will give more time on this particular topic, that is 3D bioprinting, because this is the technique of the future. So if you must know that India is like currently in the fourth position in this particular technique, like in the percentage of how much publications are coming on, or how much patents are coming in this particular technique. So if any one of you wants to pursue this area, so you might be like given this particular technique and create your tissue of interest. All right. And we are actually after US, China, and then Korea. All right. So we are very fast growing. Most of the tissue engineering labs in India currently are having their own bioprinters, and they are doing 3D bioprinting for various applications. So, and also my own research is based on this particular technique only. So I will give like maybe next class also we will discuss, we will start 3D bioprinting in today's class, but in next class also we will like touch upon it. We will give more time to this particular topic. That is what I'm trying to say. Okay, so now from this section onwards I will try to go fast, and if you have any queries you guys can let me know, because whatever I'll discuss, I'm going to discuss is pretty easy to understand. All right. So first is solvent casting and salt leaching technique. So here what we do basically, we start with the solvent within which you dissolve a polymer. So you are using a polymer. Okay, you're not using a metal, you're not using a ceramic for this technique, rather you are using a polymer. Murli, do you have any doubt? You're sharing some photos.
No, I just shared a 3D bioprinter last week in my department they bought, ma'am. So just shared the pictures.
Oh, all right, all right. So this is a bioprinter, high media.
It's from a
Okay,
Thrivima company, an Indian brand they told.
Indian brand. All right. So
Uh,
this is the, what is this structure did they make?
uh, they made a ear structure, ma'am. This was the ear one.
Here. Okay. So have you did you get the opportunity to see the demonstration of this machine?
They explained, ma'am. They told about bioink composition, how much ink bioink can we use it, how the ink will be sent
Hmm.
out by pressurization. That's what they told, ma'am. Just an overview they told, but I need to study much to understand better.
Okay, so you are in luck that you are doing this course, because I'm going to discuss all those things like how to make
Okay.
bioink, and like as I said, I will go a bit much detail about this.
Okay.
Um, right. So in theoretical part, you will learn, and then you will, when you will see in practical, like
Hmm.
if suppose you get to do it, then you will be able to better correlate. Okay.
Okay, ma'am. Okay, ma'am.
Great. That's great. So where was I? So I was starting with the traditional scaffold fabrication technique, and the first technique is the solvent casting and salt leaching. So here you use a polymer, all right, and you first make a polymer solution. And basically you have to dissolve it into some kind of solvent to make a solution, and within this solution you add some salt, which is the porogen that is going to be leached out later on to create the pores. So some type of polymers that are generally used are like a PLGA, polylactic co-glycolic acid. So this is basically a copolymer of lactic acid and glycolic acid. And salts like NaCl is used. And they are porogen and the polymer solution, that is both are mixed very nicely to create a homogeneous mixture. So that in every location of the solution you will get some salt particle, and then this mixture is poured into a mold. All right. And this polymer is then allowed to polymerize. What happens during polymerization? The solution will take the shape of the mold and will become a solid with the salt particles trapped into it. And then so usually whatever solvent that we are using is not self-friendly. We usually use an organic solvent, so we have to remove it, and we do it by evaporation. So once the solvent is evaporated, you will be left behind like with a solid polymer block or disc, whatever your mold shape of, with salt crystals trapped into it at different parts. So the next step is to remove the salt particles by leaching. So if you are using NaCl, the simplest way of removing NaCl will be to immerse your PLGA scaffold in water. So what will happen if you keep it for say 48 or 24 hours in mixing condition, the salt will come out, okay, and dissolve in the water, and uh, and you'll be left behind with the structure with the pore size exactly equal to the salt particle size, right? So in this way, if you want pores of bigger sizes, then you can use salt particles which are of bigger sizes. In this way you can control the pore size as well in this technique. This is just exactly the what I just said. It is described in a figure way. This is a solvent, all right, and within the solvent you dissolve your polymer pellets like PLGM, and then you make a polymer solution at some defined temperature and stirring condition, etc. And then within this solution you add a porogen like NaCl. You mix it homogeneously so that at every corner the salt particles are there, and you cast it into a mold. This is a mold that will create a cube kind of structure, and then you evaporate the solvent because the organic solvent is toxic to cells. And after evaporating, you will get a solid structure with salt in it. You immerse it into water and you leach out the salt particles, and what will be left behind is a porous scaffold that will look something like this when you do SEM imaging, means scanning electron microscopy. When you observe the surface of this scaffold, you will see that the black spaces are nothing but the void spaces that are created because of leaching out of the salt particles. This is how the porous scaffold will look like, which is made using this technique. So we can further process this scaffold by freeze drying it to remove all the water content. Okay, freeze drying is nothing but drying your sample at a very low temperature and at vacuum conditions. Okay, so it is good if your sample is containing some component which is heat sensitive. It is so people use this technique to preserve their drug molecules or protein solutions, etc., for a longer period of time. So we will discuss freeze drying in detail later also. And this porous polymer scaffold now can be used for seeding cells on top of it and then further culture of it. But this technique has a limitation. What is the limitation? Is that the pores that are created, they are not well interconnected with each other. So if that is the case, then then the cell infiltration within the scaffold won't happen very nicely. Now the next technique is gas foaming and salt leaching. So this is very similar to the technique that we have just discussed. Simply what we are doing here, we are replacing the salt. Okay, we are not going to use a simple salt like NaCl. Rather, we are going to use a salt that can generate gas, okay, at a defined condition. So here what we will do, uh, so this is basically a diagram of that, of whatever is written above. It is shown diagrammatically. So this is first to prepare a polymer gel kind of a mixture, okay, and people use a technique called non-solvent precipitation. So you're not using a solvent within which your polymer solution is made. No, you're not doing that. Rather, you're using this non-solvent precipitation method to create a polymer gel. Okay, and this gel will be not liquidy, like it will be like half solid or a semi-solid kind of a structure, and within it you mix a salt like ammonium bicarbonate. Okay, so here you mix a salt like ammonium bicarbonate. So in this figure, note that it is written sieved. So we can use sieves of different pore sizes to sieve out your salt particles of a particular size, right? So in this way you can control the salt particle size and thereby control the size of the pores in your structure. And then you mix these two things, the gel, polymer gel that you made, and the sieved out salt particles. You mix it and then you pour it into a mold of some kind. Then the solvent is removed. So this technique I'm actually not very much familiar with, non-solvent precipitation technique. Maybe you can look it up. But here you are not getting a solution kind of a structure, rather you're getting a gel. Just remember that. So after putting into a mold, solvent is evaporated, then you get a solidified structure, okay, where the salt again is trapped. And then you put it into an environment, okay, that will cause what? It will cause the salt ammonium bicarbonate to fizz, okay. It will uh, start releasing CO2 and ammonia, all right, into the environment. This is, so you are using an acidic aqueous solution, you're dipping it into an acidic aqueous solution. So into this solution, when you're dipping it, CO2 gas and ammonia gas will start to fizz out, it will start to come out. So when that is happening, it is going to create some kind of a path within the scaffold, all right. So you will get tunnels kind of a thing that will connect in between the pores, means promote interconnectivity. And then after this process is done, that is gas forming process is done, you take out the scaffold, all right, and then you can dry it, freeze dry it, and store it for later, or you can immediately culture cells on top of it. So this is how you can create a porous scaffold using gas forming and salt leaching technique. Now this is how the structure look like if you observe it under scanning electron microscope. So here the pores that are created, you can see they are kind of interconnected. So here this pore is connected to this, right? So here it will be connected to here. So it will be like interconnected. So this technique basically solves the limitation of the previous technique, all right. And this is like at higher resolution, 500 micron, this is at 1 mm. So here also you can see some very parts are there basically in between the pores. It is understandable from this figure, like this figure better tells you the interconnectivity, all right. So any queries so far? So Murli, I actually forgot to ask, what department, like in which college you are studying actually? Can you tell me?
Ma'am, my university name is Bharather University in Coimbatore.
In Coimbatore, right?
From
That's
Department of Biotech.
biotech. Okay, okay.
So I belong to a lab called Translational Research Laboratory. They mainly do research on cancer.
Mm-hmm.
But recently, last year, one of the new faculty came. His area of research is regenerative medicine. So
Mm-hmm.
I think he bought the bioreactor, so 3D printer. So for
3D
his
print.
research, so he is explaining us.
Okay, okay, all right. So university in Coimbatore, huh? That's very
Yes,
good.
ma'am, Coimbatore.
Okay. So that is what I'm trying to say. Like 3D bioprinting basically is the future, and more universities around the country is like looking into this particular technique. It has lots of advantages. Like it can basically change the healthcare system
Mm.
completely. Okay. So
What they told is printing will be very fast within hour we can print it, but we need to program it. That will take time. That's what they explained. He said.
okay. So can you print cells as well in this machine?
Ah, yes, ma'am.
All right. So it must have like laminar airflow and the UV chamber,
Mm.
all
Yes,
that.
ma'am.
But
Yes, ma'am.
this machine looks a bit big, or it is small. I cannot understand the size of it.
They told it is cost around 35 lakhs.
35. Okay. All right. High Media is the, I think, the parent company who made this, no?
Yes, ma'am. Yes, ma'am.
Okay, okay. Try to use this machine if you get the opportunity. All right.
Mm. What
So,
and all I can learn from that, ma'am?
yeah.
Basically, what kind of skills can I learn from this? Basically,
So,
because
for bioprinting, as we will see later on, you will learn how to make something called a bio ink. Okay,
mm,
that you
mm,
have to load it into the machine. So you have to understand what are the properties this bio ink should have. Then you will also learn if you actually operate the machine, you will have to learn CAD modeling and something like that, means to make the 3D models. And then you will have to optimize your printing process so that you can reproducibly make hundreds of structures, right?
mm,
And then use those structures either for transplantation on a body, like on human or on mice, or you can use those structures for drug screening tools. Rather than using animals, you can use those structures, and
mm.
are dispensable, like you can create again. So it is cost effective technique as well. Okay.
Yeah,
So
okay,
these
ma'am.
are some of the applications that people are doing right now using this particular technique. So
Okay,
I,
ma'am.
yeah, so I completely changed my like, actually I saw the machine and I felt very good actually, that not only IITs but also other universities are also taking up this initiative and teaching their students. That's very good. So, any queries so far in the two techniques that we have just saw?
No, ma'am.
So this was all about the leaching method. Now we will see how people are using, or people have used microspheres or macrospheres to create scaffolds. So the idea is you create spheres of particular size, like in micron size, and then you use aggregate these microspheres in 3D space, give some heating or add some solvent that will cause fusion in between these microspheres. So on fusion, what will happen? It will create the void spaces in between the spheres, and these void spaces will ultimately uh, make the porosity or contribute to porosity of your final 3D structure. So here, so this is one way, like you can first create the porous microstructures, then they are pipetted, okay, and then they are basically aggregated on top of a filter, then it is then centrifuged and then freeze dried. So this is one pathway of creating microspheres. So here the freeze drying is actually causing fusing in between the microspheres, and centrifuging is again causing aggregation, and the filter is used to sieve out spheres of some particular size. All right. So again, you have to, and these spheres are made up of polymer, okay? And then, so that for making these spheres, you have to make a polymer solution first, and then load it into, say, a syringe connected to a syringe pump. The syringe pump will allow you to control the volume of at the flow rate, basically the flow rate of the polymer solution coming out of the syringe, and you will get spheres of equal volume every time. And these spheres have to be like cross-linked. Polymer has to be cross-linked in order to get retain your spherical shape. So you use a syringe pump, connect a syringe with the syringe pump, load your solution into the syringe, and at a defined flow rate, start dispensing out your polymer solution of defined volume into a cross-linking solution. So as soon as the solution falls into a cross-linking solution, it will turn into a sphere, like bead, all right, bead kind of a structure. Then what you can do, you can in order to remove the spheres out of a solution, cross-linking solution, you can centrifuge it out, you can use a filter as well, and then you have to wash it and then freeze dry it so that they will like or you can heat it or freeze dry it, or you can use another type of solvent in order to fuse these microspheres with one another and create a 3D structure. All right. So this is how the spheres would look like if you see it under scanning electron microscope. See how beautifully the spheres are made. So the shape of the sphere depends again on the polymer solution that you are using. Also, the size of the spheres will depend the flow rate at which the polymer solution is being dispensed. All right. So and this kind of scaffold, they are used for basically cell culture, like cells are seeded on top of this scaffold, and after few days of growth, people have observed how the cells, these are the cells basically, okay, these are the cell structures, how they have like attached themselves to the spheres. Okay, so this is how the cells growing on such type of scaffold looks like under a microscope, electron microscope. Then under phase separation method, the class of technique that we are going to discuss is freeze drying, also known as lyophilization. Now this is one of the commonly used technique to create highly porous scaffolds. So what you have to do first, you have to again make a polymer solution, pour it into a mold of shape and size of your choice, and then allow this polymer solution to get like frozen. Like you can keep it in minus 20 degrees Celsius, or you can keep it in minus 80 degrees Celsius, or in liquid nitrogen. So it will freeze instantaneously. The solution will freeze. You're not immediately cross-linking it. Or you can, what you can do, you can cross-link first and then freeze. You can also do that. Okay. So after it is frozen, you have to use a machine called freeze dryer to do your freeze drying process. Okay. After it is freeze dried, you can take out the scaffold, you can wash it, all right, you can dry it further. After washing, you can again lyophilize to dry it, and finally what you will get a very very porous structure. So, and the beauty of this is the pores that is going to be created, they are highly interconnected. So how that is going to happen, I will discuss in few minutes. But first let me show you how how in literature people have used the freeze drying process to make porous scaffold. So this is a polymer solution of some weight percentage. It is mixed with another polymer solution. It is then stirred well, all right. And this polymer solution is then 3D printed to create a grid kind of a pattern. This is your 3D printed structure. So in order to give more porosity, so these pores already are there, but people want to give more porosity for better cell infiltration. That is why they are freeze drying it and then doing sterilization process. And this is how after sterilization the scaffold looks like, okay, after freeze drying. So when they observed it under electron microscope, so this is the pores that they initially created by 3D printing. They are the pore structures, and at higher resolution you can see like in between the filaments. So this is like in between the filaments, means you have they have basically zoomed in this part here, okay, to show within the polymer additional pores are created. So these are the pores that already exist, and these are the additional pores that they have created by the freeze drying process. Now how actually freeze drying is helping us to create such a porous structure, and what is happening to the polymer solution when you are doing freeze drying. So to understand that, you have to first understand the phase diagram. Okay, so most of the polymer solutions that we use are made in water, means they're aqueous solutions. So the main solvent here is the water. So it is the water that we are going to remove through freeze drying. So for that we have to understand how the water exists in the three phases: the solid, liquid, and the vapor phase. And that concept is coming from the thermodynamics, that is the phase diagram. Okay, so here these curves are the equilibrium curves. So this curve is the solid liquid equilibrium curve, this one. This is the liquid vapor equilibrium curve, and this is the solid uh, vapor equilibrium curve. When we give temperature and pressure, okay, at defined temperature and pressure, we can bring water at a state where it is like neither completely solid, neither completely liquid. Okay, these two states are like coinciding. We can at a defined temperature and pressure. Similarly, this point is called triple point. This is very unique point. Basically, at this temperature, that is 0.01 degree Celsius, and at a pressure of 0.006 atmospheric pressure, you can get water which is like having the properties of solid, liquid, and vapor. Okay, that is the triple point. But for freeze drying, we are actually interested in this curve. Okay, where the solid and vapor are in equilibrium. Okay, so at a and this curve is obtained, you see, at a very low pressure, almost vacuum, and a very low temperature, like negative temperatures. So you can get the equilibrium between the solid and liquid when the pressure is very low, like and vacuum condition, and at a very low temperature. Okay, so first like what we do, we take a polymer solution, we freeze it, right? So before freeze drying, we should have a block of polymer that is completely frozen, because during freeze drying, what we are going to do, at a very low pressure and temperature, we are going to start the process of sublimation, where the water which is in solid state, that is in ice, that is directly converted into vapor state. Okay, and that can be only achieved when you give temperature and pressure that lies along the sublimation curve or the solid vapor equilibrium curve. So in this way, when the so in the polymer solution you have made in water, so the water molecules, they are trapped into the solid block of polymer. And when you are doing freeze drying, that is you are starting the process of sublimation, the ice that is formed within the polymer block, that is directly converted to vapor, so they leave it. And what they create void spaces, they create pores. And when they leave it, they leave tunnels, like interconnected. They connect the uh, paths, they create new paths basically. That is why the pores that are created, they are very interconnected. Okay, and the structure that you get out after freeze drying is highly porous. So is there any doubt in understanding how the freeze drying is working, or how actually you get a porous structure through freeze drying? Any queries so far?
No, ma'am.
All right. Okay. I hope others are also understanding. Only Mulli is responding. So can I assume others are also understanding and are in the same page?
Yes, ma'am.
All right. Great. So next technique is under the group of fiber-based methods, that is electrospinning. So when we are trying to mimic the fibrous nature of the tissue, we use these type of techniques where this artificial ECM or the scaffold is made by arranging uh, nano scale or micron scale fibers. So the electrospinning technique will give you nanoscale fibers. All right. So here in this technique, what we are doing, we are first going to prepare a polymer solution, load it into a syringe, and connect the syringe to a syringe pump. All right. This syringe pump is used to control the flow rate at which the polymer is going to be dispensed out of the syringe. And that what we do, we expose the coming polymer solution that is coming out of the syringe to a very high voltage. Okay, so the setup has a electric field. One end of your like the positive end say is connected to your syringe, and the other end is connected to a depositing area. So what is happening, due to opposite charge, the polymer solution is coming out. Okay, and it is stretched, and as it is deposited as a fiber. So it will become more clear from this image. So this is your syringe containing your polymer solution, and it has a needle connected to it, and you know needle is made up of a metal, and you connect this needle with the current supply. And basically then what will happen, whatever polymer solution is coming out from the needle is having some charge. All right, and these highly charged polymer chains, they will try to like get rid of this charge, right, by getting attracted on an oppositely charged surface or on an earth surface. So that surface is called a collector. Okay, and this collector can either be oppositely charged or it is connected to earthing, and you have to basically keep it close, means you cannot vary you can only vary the distance between the needle and the collector to a certain range. If it is too far, the collector is too far, then the whatever polymer solution that is coming out from the needle won't be stretched in form of fiber. Okay, or if you keep it too closed, then the fiber formed will be like liquid only. All right, it won't be, it will spread, it will spray basically, droplet type of structures will be formed, you won't get fibers. So here we have to optimize the distance, then we have to optimize the charge, how much charge we want to give to a polymer, that is will be controlled to the voltage, okay, of your current supply. And when you see how the fibers look like under ECM, under SEM, scanning electron microscope, you will see that they are having like tubular fiber like structures. So this is how the electrospinning works. All right, so we are giving some charge to a polymer solution and keeping it close to a opposite charge surface. So then what happens, the polymer is getting stretched and forming nanoscale fibers or micron scale fibers as it is getting deposited on the collector surface. Okay, so this is a diagram showing how if you change the setup of your printing, not printing, of your electrospinning, you can either create aligned kind of fibers, means you can create a scaffold where the fibers are completely aligned to each other in one direction, or you can create a scaffold where the fibers are randomly arranged. So depending on where your what type of collector you are using, if you are using a rolling drum, the drum is continuously rotating, then what is going to happen, the fibers that are deposited, they are also spin, like हम लोग kite उड़ाते हैं ना, so that spool is completely rotated, so that whatever thread there you're putting on, they are arranged sequentially in one side by side. Similarly, if you rotate the drum, if you're using a rolling drum as a collector, the deposited fiber will be aligned in the same direction. Or if you use a stationary surface as a collector, then whatever fiber that will be deposited, they will be randomly arranged. So when they are aligned, you can better mimic the tissue structures like muscles, right? Or if they are randomly arranged, then also you can mimic some like vascular kind of structures, okay, where you can mimic the complex network of microcapillaries in the tissues. So this is how electrospinning can be useful to create scaffold for your tissue of application. So whatever I have said so far is written here, but let me just highlight this point, that while you're using this technique for making your scaffold, you have to keep in mind what are the influencing factors. First is the flow rate. What is the flow rate at which the polymer is pumped out? Then the viscosity of the polymer solution. The solution is very viscous, then you will have you will have a higher chance that it will clog the needle. All right. Or if it is very low viscous, then what will happen, it will rather form drops. So it is the viscosity matters here. Okay. Then the diameter of the needle, depending on the diameter of the needle, the fiber diameter will change, and also the voltage, how much voltage you are using. Okay. There are other parameters also, like the humidity. So if your material property changes with humidity, or the electric field can change with humidity, so you have to maintain within the chamber, the humidity level should be maintained. Also the distance between the collector and the syringe needle will again determine how the diameter of the fibers is changed. If the distance is too high, then the fibers will stretch more, resulting in a smaller diameter fibers. If the distance is smaller, then the diameter will be bigger. All right. And depending on the collector, you in type of the collector, you can either have aligned a fibers mat, or you can have a mat where the fibers are not well aligned. Okay. So up to here, we have basically covered two topics, or two techniques under each of the traditional methods that are used for making scaffolds. And like briefly, I have also explained about decellularized matrix. Again, I'm coming back. So here, what we do, we take a native tissue. It can be either from an animal or from human. Then we remove all the cellular components from it, and we can do that either use chemicals or using physically, like physically scraping out the cells. Okay. And then we will have to also remove all the toxins that might be there in the native tissue. After doing all these treatments, you have to still make sure that the ECM that is left behind, it should have mechanical stability. Okay. It should not crumble, it should not break. So your treatment process should be gentle enough to preserve the 3D structure of your ECM. And after you are done with it, you can then provide the cells of interest on the top of your ECM. Okay. And then culture it as you would do in other cases as well. Okay. This is how you can use a decellularized matrix to as a scaffold to make your tissue of interest. Now, as promised, I will be now discussing in detail the technique called 3D bioprinting. All right. So, is there any query so far, or anything that I have missed to discuss and you want me to repeat? Anything like that? Okay. So, if we look into how the scaffolds are being made, so we can actually categorize the basic approaches into two types. One is the uh, top down approach, another is the bottom down approach. So in top down approach, what we do, we prepare the scaffold first, means we prepare the 3D structure using a material first, and then on top of it we seed the cells. So we are starting from the top and then we are going to the down, means a higher level is your scaffold, and then the smaller component, the cells are added later on. That is called the top down approach. So but this technique or this top down approach has a limitation. What is the limitation? Here when we seed cells on the scaffold, we cannot really control how the cells are going to distribute themselves, all right, within the 3D space. We cannot control that. Also, um, cells, how the cells is going to degrade the material and then remodel the scaffold, okay, and create their own ECM. So these things also we cannot really anticipate, okay, how it is going to happen. So that is the limitation of the top down approach. Whereas there's another approach called bottom up, that is we start from the smaller component of the tissue, that is the cells, and then we go to the highest component of the tissue, that is the scaffold, the bigger component, okay, the ECM. So people first make smaller like units of cell and material, okay, and then use this smaller unit cell and material to ultimately build the tissue. They are combined together and create a larger scaffold. So here what will happen, the cells, as the cells will be distributed in the 3D space along with the material, you can actually control the cell distribution in a better way than the previous approach. You can actually control this because you are basically manually, you can say, you can think of, you are manually arranging the blocks of cell and the material in your own way to create a 3D space. So you are controlling the cell distribution. Also, cells are like encapsulated within the material. So the material and the cell, their growth, the cell growth and the material decomposition or remodeling, those are happening simultaneously, okay. So we have a better chance of mimicking the ECM architecture that is there in native tissue using this approach, all right. So any query in understanding these two approaches? So if we look into what all techniques come into what type of approach, so the techniques like electrospinning, freeze drying, solvent casting, solid leaching, then self-assembly, 3D printing only. So these all techniques come under top-down approach, right? We were first in the electrospinning on solvent casting, solid leaching, etc. We were first making the scaffold, and then later on we will be adding cells on it. Also, if you look at the technique called 3D printing only, okay, where the cells are not used, only the material is like deposited in a predefined like 3D structure. There also we are making the 3D scaffold first, later on the cells are added. So if you remember the freeze drying example I gave, so here in this work, so here actually people are doing 3D printing. The material is loaded into a 3D printer machine, and it is the tip is moving in XYZ direction, and it created a 3D structure that looks something like this, okay. So on the top of it, later on people will add the cells and culture it further. So this is a top down approach. Whereas the bottom up approaches is the bioprinting, 3D bioprinting, where you like take a material, add cells, okay, into that material, and make your unit cell material mixture, okay, and then you use that mixture to create your 3D shape. Another technique is called self assembly. So here material properties such that it can self assemble, means the polymer chains, it attracts one another through various attractive forces and create a 3D space. So we will not discuss self assembly in this course, but if you are interested, maybe you can look into literature and find out more, okay. Another technique, that is soft lithography, is also used, and it also comes under the bottom up approaches. So we will focus on 3D bioprinting from here onwards, which is a bottom up approach. So shall we take like a 5 minutes break and then we'll meet then?
Okay, ma'am.
All right. like join the meeting in 5 minutes. Okay, means don't leave the meeting. Just you can go to washroom, drink some water, and then come back in 5 minutes. All right. Hello, have you joined the meeting? Have all of you joined the meeting?
Yes, ma'am.
Yes, ma'am.
All right.
Yes.
So let's continue then. So as I discussed, like 3D bar printing is an additive manufacturing technique. So if you look at the manufacturing process, you can do it in two ways. You can either take a solid block and carve it out, okay, to create a 3D structure of your desired like type. That is called subtractive manufacturing. Another way is you take your material and deposit on top of one another, okay, like layer by layer, and then finally what you will get a 3D structure of your desired type. That is called additive. When you're adding material, uh, then is called additive manufacturing. When you are removing material to create a 3D shape, that is called subtractive manufacturing. So you can imagine sculpting is a supporting manufacturing, whereas a 3D printing, okay, so I'm sure you guys have seen how 3D printing happens, like in videos or in movies, etc. So that there people add like material, okay, polymer, it can be polymer, metal, etc., like anything. Even cement, civil engineering people, they can deposit cement, okay, over one layer over another and create walls. That is called 3D printing, okay. So bioprinting is also a type of 3D additive manufacturing technique, but here what we are interested in, we are interested in capturing the complex architecture of our tissue or organ, okay, and that too in vitro, outside the body. That's why we are interested in this technique. And for doing this technique, you have to first make a ink, and here it is called a bioink, and it is made up of a biocompatible material. So people generally use a hydrogen material, which is basically a polymer, all right, and they add cells into it or some bioactive factors like drugs or growth factors, etc., with the cells or without the cells. So and then they make a bioink, that is called the bioink. Then this bioink is deposited layer by layer to create a 3D model or a 3D shape. Okay, now conventional 3D printing, where only the polymer solution or a hydrogen solution is deposited layer by layer, that is the conventional 3D printing, and that happens cell free, means you are not adding cells or you are not mixing cells with your material, and it can give you cell free scaffolds. So in this way, then the conventional 3D printing technique becomes a top down approach way of designing scaffold. Now the bioprinting, there are various factors you should like keep in mind while thinking of bioprinting a tissue or organ. First, what material you are going to use, okay, the property of that material you should know. Then the cell type, what type of cell you are interested in printing, either it is stem cell or primary cells or some cell line, all right. Then if you are going to mix some bioactive factors, what are those bioactive factors? If they are cytokines, chemokines, it means they are protein in nature, right? Or you can add some genes, okay, or you can add some drugs. So the printing conditions will vary accordingly. Then you can add some other molecules as well, like nanoparticles, suppose, okay, uh, to add some additional functionality into your scaffold. Or and also you need to know, means your choice of material, or your how the bioink properties will be decided. That will depend on the printing technology that you are going to use. So 3D bioprinting, it can be done either via extrusion, okay. So I will again discuss what are these technology later on, but briefly, extrusion, here you are using a nozzle or a needle, and through which you are uh, like on application of force or some application of pressure, you are basically pushing out the material to form filaments, or you form fiber kind of a structure, and these fibers or these filaments, they are deposited on a surface. Okay, so that is called extrusion. Or you can use light, okay, to and this light falls in all xyz direction to cure your, or you to to cause polymerization of your material, and thus create a 3D shape. Or you can use drops, means droplets. Your printer ejects droplets, and these droplets, they are like allowed to fall on the substrate in a like proper shape, it in a square shape or a circular shape. And then when they add on top of one another, okay, you have to give some substrate to a drop will otherwise merge, like a biopaper, something like that, between two layers of drops. And in this way you can create a 3D model. So what, depending on the printing bioprinting technology that you are going to use, your bioink properties, means bioink containing these three components, overall property of the bioink, it will vary. Then the printing conditions also you have to keep in mind, because the printing condition, it will affect various things. Okay, it will affect how good your shape is looking after printing. Then the cells, if you are using cells in your bioink, then cells are very very vulnerable to the stress, the shear stress, or very high very high wavelength of light, what wavelength of light you are using, that can be cytotoxic. Or if you are using droplets, then the drop if the droplet is splattering on the surface, the cell can also break. So depending on what means what printing technology you are using, along with what type of bioink you are using, your printing conditions has to be optimized, so that you can maximize your cell viability in the printed structure. You should be also be able to maximize the quality of your 3D print. Okay, you'll be able to like see all the pores very nicely. Then the structure doesn't merge, each layer doesn't merge from one another. That is a very special term is given, that is shape fidelity is better, okay, or printability is better. So we will actually discuss these terms later on, but just for now, keep these particular points in mind. So bioink is basically made up of these four types of materials. Okay, yeah. Now, the 3D bioprinting as a technique has various applications, and in literature, people have reported it for organ printing. Means you can make a tissue or a small section of an organ by using 3D bioprinting. And people have already attempted it basically. They have tried to create skin structure, bone, then vascular grafts, then trachea, then heart tissue, cartilage, etc. Liver also, small liver models, etc. So these are all their bioprinting has been attempted by researchers all over the world. Also, you can use the bioprinted tissues as a models for research. Means you can create cancer models to study how cancer progresses, or you can study some other type of disease, like you by using the 3D bioprinted tissues. Or you can also use it for drug screening and drug discovery purposes, as well as you can use it for uh, testing the toxicity of some drug or some other chemical of cells, okay, on cells, and later on see whether that chemical is suitable for human consumption or not. Means for toxicological studies, then for drug discovery, for research purposes, these bioprinted models can be used. Now this technique has various advantages on its own. First is, it allows the user to, under optimized condition obviously, to control the cellular distribution. Okay, and also the distribution of the cell can happen at a very good resolution, means at a distinct level the cells can be present. If your bioink is having very good properties, very good properties, and your that is appropriate with your printing technology, then you can actually create a structure, say a cube kind of a structure you can create, where each of the layers you can add different cell type, 1 2 3, and each of the layer can remain distinct from one another, so that you can say, if you're trying to mimic a skin, all right, you know how the skin has different layers, so you can actually create those layers individually, where the cells, the morphology of the cell will be different in each of these layers. Okay, so this is possible when you are using an optimized bioink formulation, okay, for your bioprint technology. Then it also offers scalability, means you can create very small structures like few mm's, or you can create very big structures like in meter scale, okay, means depending on your application you can create very small or very big structures. Then reproducibility, means if you just optimize your bioink formulation, okay, and you are successful in preparing that bioink every time, and you have like also observed for this bioink preparation, the bioink prints very well at some printing condition, and then you can repeat it as many number of times you want, okay, and you will get the same kind of structure every time. So it is a highly reproducible technique, but yes, some skills are required to achieve to that much level of reproducibility. Then it is a cost effective technique. So if you're designing your own bioink, okay, with starting from the material and then the cells, etc., then overall cost of the tissue construct prepared, means you can calculate the cost uh, means used up for making one tissue construct, you will see it will is minimum in comparison to other techniques that we have discussed. Like we are not discussing just cost in terms of money, but also cost in terms of your time required to make that tissue construct. So in those two aspects, time and money, this bioprinting technique is actually cost effective in comparison to other techniques. But currently we haven't been able to reach to that level that we can make the technique cost effective. But when you're talking about high throughput screening, or when you're talking about manufacturing hundreds of tissue constructs at a time, then this cost effective factor will be very big, will play a very big role. Okay, and but this technique also has its own challenges. So whatever printing conditions that you are using for making your living tissue by this technique, uh, it should not harm your living cells. So in extrusion, the cells are exposed to shear stress, and the shear stress can cause cell death. Also, if you are using light of a wavelength that is toxic, then also your cells can die. So you have to make sure your printing conditions should be cell friendly. That's it. Then another so basically these two challenges are basically challenge of the tissue engineering field, not just bioprinting. Bioprinting will actually help you to address these two challenges. So people currently are now trying to create tissue constructs with inbuilt blood vessels in it. So what will happen, you are instead of having only interconnected pores, you want capillary kind of structures that gives easy path for the nutrients and the oxygen to flow to individual cells. So and these kind of vascularized structures, what will they will do? They will allow better integration with the host body. Means the blood vessel kind of structure from the tissue, it will basically stitch up very nicely with the blood vessel of the host. And innervenation, you know what is innervenation? It means growing of neurons basically. Okay, so people are also trying to like create artificially within the tissue construct neurons, and in that way, in the affected areas, the damaged nerves can be basically repaired by the neurons that you have created in your artificial tissue. So often what happens, if your injured area is a very big area basically, and after repairing, that area loses its sensitivity to touch, or some it doesn't it doesn't feel like normal, like say skin. Okay, so it doesn't respond to some stimulus very nicely. So people are trying to incorporate these two um, as well into an artificial tissue, into a tissue engineering construct, the vascularization aspect as well as the nervous tissue aspect, so that we can better mimic the in vivo organ environment or tissue environment. Okay, so bioprinting can actually help us to do that. So basic workflow of how one should start doing a bioprinting. So first thing one should do is do imaging. So if you're interested, your final goal is to make a tissue construct that is going to go and be transplanted on an injured site of a patient, then you want to make sure that you know the dimensions of that injured site very well. And for doing that, you have to do imaging of that particular site. You can either do MRI, you can do CT scan, or you can do ultrasound. Okay, or you can use a 3D scanner as well to get images. And these images are actually stitched together. Okay, and created a 3D structure using some software. So and that 3D structure can be further processed. It can be further processed, so that image will only be able to tell you, from the images you will only be able to understand the, say, the boundaries of the injured site. If you're talking about skin, then you'll be able to know the boundaries of the injured injured skin tissue. But if you want to fill in the bulk of that model, you have to do it yourself, because currently the technology in this area, that is imaging and modeling, is still lagging. So it falls upon the researcher who is working upon this to understand, first theoretically understand how the tissue architecture is from literature, from books, etc., and try to do modeling in order to incorporate those means incorporate, or you can correct as well, you can correct the software mistakes by modeling. And once you are done with 3D modeling, you have to do slicing. So the 3D printer or 3D bioprinter, it is going to what? It is going to deposit the material layer by layer. So your 3D model has to be sliced into those layers, so that the machine will follow those layers, and in each layer it will deposit the material of some defined uh, architecture. Okay, and ultimately what you will get a 3D structure. Okay, so this is your pre-processing part. Before printing, you have to first do imaging of that particular injured area, and then you have to do 3D modeling and slicing. And the second step is the processing step. So in this step, you have to prepare your bioink. So as you know, as I already mentioned, bioink is nothing but the material and the cells. Additionally, you can give some growth factors and nanoparticles or drugs, molecule, etc., into your bioink. And this bioink and is then loaded into a 3D bioprinter. So 3D bioprinter, we have to also load the CAD model that we have made. So the CAD model that is loaded in a 3D bioprinter is in .stl format. Okay, so this stl file is read by the printer. Okay, so HDL file is read by the printer, and you have also loaded the Bioink. Now the only step left is to start the bioprinter. It will start printing according to the 3D model that you have given, and you will get a model that looks like your CAD model. Also, don't expect that the obtained structure will look 100% like your 3D model, because the material that you are using is hydrogel, so the corners or the lines won't come very sharp. Okay, so also, if your material is not very well optimized, then what can happen? It can actually the layers can fuse with one another, and you can be left behind with what is called that looks irregular, that looks say 30% like your 3D model. Okay, and then the last step that you have to do, that is the post processing steps. So you created your tissue construct by bioprinting with cells encapsulated in it. You take that and you have to culture it. Okay, so it is just like culturing the cells with the scaffold that we have discussed previously. You have to give some suitable media conditions, and then if you are flowing the media, then you have to give some suitable flow conditions. Okay, you can either culture it in a small scale in petri dish, or you can use bioreactors if you are making so many tissue construct at a time. And then you have to allow the tissue to mature. Means maturation means the cellular rearrangement, the ECM remodeling is going to take place, and then if you're looking into say skin structure, then the stratified layers will be formed. Okay, so these all steps has to be done, and after maturation your tissue is now ready for implantation on your injured site. Okay, so these are the three steps, this is the workflow of how you one should start with the 3D bioprinting process. Okay, any queries? Okay,
Yeah.
No.
so this slide basically says exactly the same thing that I have discussed, so you can look into it afterwards. Now, I will not go into detail of CAD modeling, okay, because that is something that I'm not an expert myself. I am still learning, but also that is not the scope of this course to teach you about CAD modeling. You can learn it from elsewhere, but also like initially what people are doing currently, they are starting with simple structures like a square mesh, circular mesh, like these kind of structures. And I think who knows very simple drawing, they can do that. Okay, they can model it. So we haven't yet reached to that level of complexity that we are making the um, architecture of our organ completely in CAD. Okay, we haven't yet been able to reach. That is where we're taking help from the imaging to able to like truly capture that native architecture. Okay, so that is why I'm not going into detail of the CAD modeling part or the pre-processing part. I will directly jump into the processing part of the 3D bioprinting workflow. So here what we have to do, we have to first make a bio ink. So if your lab has lot of money, you can directly purchase it. Okay, that's an option that is always available to a researcher. But if the your lab doesn't have the resources to purchase it, then yes, you have to make it yourself, and making it yourself is much more again cost effective. So bioink is a mixture of a biomaterial, so we generally use a hydrogel material. Okay, because why we prefer to choose hydrogel. Anyone? We have discussed what are hydrogels. So can anyone tell me why um, we prefer to use hydrogels for culturing cells? We have already discussed it.
They are hydrophilic in nature.
So
It is easy for the cells to uh, intake the materials, exchange of materials.
okay, you're partially correct. Means you're trying to say the correct answer, but not been able to. Anyone else would like to try? Try try to answer it correctly. Okay, uh, that makes you that makes you more credible. People will believe what you are saying. So anyone else would like to try? So hydrogels are basically a special class of polymers which have the unique property to absorb water. Okay, because they're hydrophilic. So they can absorb water and swell a lot. So when we encapsulate cells into hydrogels, then we will be able to mimic the aqueous environment that the cells already exist in our body. So that's a simple reason why hydrogels are generally preferred for like culturing cells in tissue engineering. We can use other classes of material as well, like ceramics or metals, something like that. But again, it limits to the tissue type. Like we can use metals for say bone, okay, or ceramics also for bone, where we are not looking into a architecture where the cells are present in a aqueous environment, but when we are trying to mimic the soft tissues, okay, where the cells are always in contact with blood vessels around it, and in a continuous exchange of material is going on in the water aqueous environment, then we are opting for a material which belongs to the hydrogel class. Okay, so, so usually bioink is made using a hydrogel material, but there are other examples as well where people have used other biomaterial. But again, it depends on the type of the tissue. And with this biomaterial, we mix a biological component. We can mix a cell, okay, cell type, or we can like mix cell media with serum in it, then genes, other type of proteins, growth factors, like whatever you want to help your cell growth, or whatever is suitable for your application, you will mix with that hydrogen and make a bioink. Okay, simple enough. Now people are also trying to make a scaffold, or also trying to achieve scaffold free bioprinting, where in the bioink no material is there, only liquid is there, liquid media with cells suspended in it. The cells can be in aggregate form or in spheroid form, okay, or in like tumoroid form, like only cells and the medium, that's it. But it has a limitation. So when you try to bioprint this type of bioink, then the resultant structure won't have the desired mechanical stability. Okay, so if your a purpose is for transplantation, so this type of tissue structures won't help. Okay, but the plus thing about it is you can get a higher cell density. And another negative point that I feel is the viscosity, the overall viscosity of the bioink will be like water. Okay, so it will never form filament kind of structures. You will have to look for the printing technology that suppose the formation of droplets, and then using drops you have to assemble your structures. So that's again adds to the complexity, and then obviously mechanical strength won't be there. Okay, so depending on the application that you're looking for, you will choose the printing method. You can either use a bioink with biomaterials, or you can use scaffold with bioprinting. Now, important material properties that one should look into while making bioink is the bioink made bioink. It should have the property of printability. So, what is printability? In one line, printability is the ability of the material to print. Okay, it's a very like simple thing to say, but it has more meaning to it, and we will come to it in the later lectures. Okay, then the resultant material should be biodegradable. So that's a requirement for all materials that are used for tissue engineering. It should biodegrade, and then it should also be cytocompatible, means it should support cell growth. And one major challenge while making bioink is actually successfully mixing the cells with the material. Okay, that's actually a challenge. If your material does not have, or if your material is very viscous, it means polymer solution is very viscous, then it is going to be difficult for you the to mix your cells in it. Okay, and if the cells are not well mixed into the bulk of the material, then you won't be able to uh, encapsulate it, and as I said, you won't be able to make a unit of cell and material. Okay, so what will ultimately happen? Cells will be at the periphery. Okay, material will be say in the bulk, and your cell distribution is not going to be uniform. In some areas you will see more cells, and in some areas there is not going to be any cell at all. Okay, so your whole purpose of why you're doing bioprinting will be defeated. So what is ideally required is, like, what should ideally happen? Ideally, we want a bioink that should require no pre-processing and post-processing steps. Means while making the bioink, we should not be able to do any pre-processing techniques. Also, after printing, we should not be like it should not require any cross-linking steps to uh, create a solid structure. But this is an ideal case. uh, Currently, whatever available in literature regarding bioink preparation, everyone is doing cross-linking after printing. Also, they are functionalizing their material so that the material becomes printable. Okay, that is, they are pre-processing it, and then they are using that material. The material should also have a desirable viscosity. Okay, that would allow homogeneous mixing of the cell. Otherwise you won't be able to control the cell distribution within the 3D construct. Also, it should allow faster mixing basically. Okay, because if your material say takes more time or requires heating for same, if your material requires heating to lower its viscosity, and at a high temperature only its viscosity is low, and then you add cells into it, what will happen? Cells will experience heat shock and they will die, right? So uh, at room temperatures you should be able to mix your cells within the material, and that too should happen in a faster way. Okay, you can use some stimulating factors, like you can maybe mechanically stir in your cell suspension within the material, something like that. Okay, now for creating a cell laden bioink, the cells and other water soluble components, they are usually suspended in aqueous solution. Okay, keep this point is important actually, means important for you to understand. So oh, the cell suspension is basically nothing but a aqueous solution. Some water is there, right? Water and hydrogel. When you're making hydrogel, the solvent is also water. So when you're going to mix this cell suspension with your hydrogel, then overall solvent content will increase, means your water content is going to increase. So it can cause changes in the property of the overall bioink, means its viscosity can change. Okay, and then what will happen, it can also affect the cross linking mechanism. It can make the mechanism slower or faster. Okay, and it can also affect how much the hydrogel can now swell. Okay, so overall bioink property can change depending on how much cell suspension you are going to mix with your material. So any queries till now? So that's it for today's class, and in the next class we will continue with the same topic, bioprinting, and we will finish up the bioprinting topic, and then we will briefly discuss about like using growth factors for tissue engineering purposes, how you should how you can deliver the growth factors in your scaffold for like your intended application. Okay, so we will discuss that, and then we will also cover up briefly about bioreactors, means if in future yeah, like bioreactor is one very essential part, and not many biotechnologists actually understand the potential of bioreactors. They most of the research just stays in the lab scale. Okay, and like in the tissue culture plates and battery plates, but we have to think of upscaling our research. So that is why we should know how the bioreactors work, and we should be familiar with this concept, so that we are not afraid of using it in our research. Okay, and after discussing the bioreactor part, and also I will cover briefly about how the host reacts when a foreign material like say tissue engineering constructs is implanted. So how the um, in our immune system responds to it, and etc. We will briefly discuss that as well, and after that we will finish up the course. And as I mentioned, we will have a final quiz, most probably on 16th. If it is delayed, then I'll also let you know, because that in that final quiz I want to cover up all these topics, final topics. Okay, and that quiz will contain the syllabus starting from the topic that we were discussing after the quiz 7. After quiz 7, yes, we had quiz 7, right? So after, sorry, quiz 6, sorry. After quiz 6, whatever topic was discussed up to the bioreactors and the last class, up to the last class, the entire syllabus will be there. So I will give you some time for that quiz. So if our classes get delayed, like say, if we are not able to complete till 13th of next week, means Monday, then we will have few more classes. But after the classes get over, maybe I will give you some time to prepare for that final quiz, and that final quiz will be a long one, like around 2 hours. So try to prepare for it well. Okay, because I don't know next time when you will be able to study this course. Okay, and I hope whatever you are studying is going to be helpful in your career, or help you going to decide your research career ahead, or your corporate life, because many companies now are also looking for people who knows about tissue engineering. So yeah, that is going to be very helpful if you study well. And I have only received project from one group. That actually sad to see, means why only one group. So two other groups, they have asked for extension. So Murli, I think you messaged me, you were supposed to submit it
Yes,
today. Yeah,
we will
me.
submit now.
Okay, so you guys will submit today. And
Yes.
the okay, and the group with Harshita, and who else, Harshita, Aditya, Nidhi. So this group I had asking for a extension till 27th. So I have actually permitted them, but please do it on 27th. If you're not going to do on 27th, then sorry, I won't be able to consider it. And it's like, I think you are starting now. That is why you're asking for 27th, because it's a very long period, starting from today. So I don't know why you haven't worked yet. I was insisting that you start working from the beginning of this course. That is why I distributed the group very early on. All right, but since this is my first time teaching this course and you guys are my first students, so I'm giving you a lag, but maybe future students won't get this lag period. Okay, and if there are any queries, let me know related to anything. Also, I will at the after the final quiz, okay, I will like share with you your individual scores that you have obtained over the period of course, combining everything, okay, like the project and the quiz evaluation assignment, everything. And I will also speak with ISSS people to get to certificates as well as soon as possible. Okay, any queries?
Yes, ma'am. Ma'am, if possible, can you please delete the quiz for like preparation because this week is like all like festive season, like Bhai Dooj, Diwali, so we have no time.
Okay, okay. So you are suggesting that don't do the quiz on 16. That is what you're trying to say?
Like after 20 or 21, 22, anything.
Okay, okay. I'll take the suggestion into consideration, but maybe we will have classes. All right, in between. In between, we will have classes. Try to join those classes. Okay. I will give you some time. Don't worry. I will give you at least 1 week to study for the quiz because the syllabus is too big for this quiz. So I'll give you 1 week time. So and like before 1 week, I'll finish up the syllabus. Then only the quiz will happen. Okay. Anything else?
Ma'am, the syllabus for the quiz is after the quiz 7 or 6,
Say
ma'am.
six after the that was the last quiz 6. After that, the topics covered will be there in your final quiz up to the last class.
Okay, ma'am.
Anything else?
No, ma'am.
Okay. So just let me take your attendance quickly. So who all are present, kindly respond with their names.
Murli, ma'am.
Okay, Mulli next. Hmm?
Kirtan,
Kirtan. Okay.
Vani, ma'am.
Vani. Okay. Next. So I've marked Mulli, Kirtan, Vani. Are you physically present or just virtually present?
Janvi Sharma.
Janvi. Okay. Janvi is there. Who else?
Priya.
Nidhi Priya. Okay. Who else? Harshita, Aditya. No, are you guys there? So Shambhavi, Vaishnavi, are you guys there? I think Shambhavi is present virtually, not physically. To check that only I call for your names, not just directly mark your attendance based on the record of this meeting. Hello Shambhavi, are you there? If you are there, kindly unmute and respond. Apparently she is not there. Okay. So I've only marked for Nidhi, Vani, Janvi, Keertan, Molly. All right. Uh, okay. You guys can now leave the meeting then. I'll see you on Monday, that is on 13th. I hope I'm not ruining your Diwali with this class today. And Monday, you guys will be able to join, right? There's no commitments, like family commitments.
Ma'am, Monday I'll be traveling, ma'am.
Okay, Monday will be traveling. Anyone else has any commitments? Okay,
No,
okay.
ma'am.
No, okay.
Ma'am, can we have the class in the afternoon or
Yes, ma'am.
After,
sometime? Yeah.
okay, means you don't want the class in the evening. Yeah, that's what you're trying to say.
Yes, ma'am.
Okay. I think it will not be possible because I usually do my thesis work in the mornings, like whole day, starting from 9 to evening. So that's why I keep the classes in the evening, like after 7. So can we then do it on Tuesday? Then Tuesday evening, if it's fine, 7 to 9.
Yes, ma'am.
Yes, ma'am.
Okay? Okay. Then we will meet on Tuesday, 7 to 9 instead of Monday. All right.
Thank you, ma'am.
Okay.
Thank you, ma'am.
Yeah.
Happy Diwali, ma'am.
Yeah. Happy Diwali to you too.
Happy
Sir.
Diwali, ma'am.
Mm.
Happy Diwali, ma'am.
Happy Diwali. Enjoy if you are at home, enjoy with your family. If you're in hostel, enjoy with your friends. Chalo, bye.
Bye, ma'am.
Bye.